Okay. Yeah, it's recording now. All right, so I think many people said we should solve this. Okay, I'm gonna start solving this one. Oh, let me mute everyone. Put this there. Okay, so I'm gonna start solving this one. Somehow I should see, keep this here. All right, I can do this. So if you raise your hand, I will see it here, right? Okay. So while I'm solving this, if you have a question, just raise your hand. Okay, so I'm going to be solving homework 2C, right? The one with the rope. So let's see. So the problem is, so you have this thing here. There's a rope here, right? And there's a distributed load, right? W, distributed load, L, and there's a P. And there's a P here, right? Seeing some stuff on the chat. Okay, you guys are trying to figure out the raise hand thing. That's a good thing. Okay, so I'll continue. I hope you guys can figure it out. So you see, this is a rope, right? So I'm gonna be following the methods that that I've written on my notes, right? So I had 3 methods of doing business when it comes to shear and moment diagrams, right? So we also have one of these here. So as I wrote there, I said that step 0 is what? Step 0, when you want to do shear and moment diagram, step 0 is finding reactions, right? Finding reactions. So let's see what this rope does for us. All this rope means it is that you can only have tension, right? So basically, if I had a beam that looked like this, and it had one of these with a 45-degree angle, which is what the angle here is. These two would have the exact same procedure for solution. You know what I mean? So again, I mentioned if you have questions, just find the raise hand button, right? And just let me know. Let me see. Okay. So if is this exactly the same as the rope problem? The solution procedure is the same. What is different is that when you find this force, if I call this R, if you find that R, if I call R, if you find that the force, this force is in this direction, right? This means that if it was a rope, it would be in tension. So you would have a force. But if you solve this problem and you find that R is like this, it would mean that you have compression. So your problem changes. You don't have any force here now if it was compression, right? So your problem would be basically this one. With nothing here now, right? but this would be unstable. So it has to be compression for this particular problem. It has to be in tension for this particular problem, right? There is no other choice. So basically what you do is you just draw the beam. You put one unknown force here, call it R. I put the equivalent resultant for the distributed load in the middle, right? So I have R, I call it R3, let's call it T. So I have T, I call this one R2, I call this one R1, right? So I have three forces. So we always have to be smart about where we take our moments about. So I choose this point, right? So I call this A. So I want to write sigma M about A equals 0, right? Let me put this on the left. All right, so I want to take the moment about A. So whenever you're taking this global moment equilibrium, right, the sign is completely arbitrary. So I'm writing equilibrium equations for this segment, right, this part, which is the whole structure here. So I can just take this one or the other way. So here I take this one. So the other thing I do is I decompose this force, this T force, in two directions. If I decompose the force, so I have 1 WL, I have T over square root of 2, T over square root of 2. These two are what? T cosine 45 and T sine 45, right? Any questions so far? If you can't raise your hand, you can also let me know in the chat, right? So no questions? All right, I'll move forward. So, oh, I saw something. Okay. Thanks. Someone mentioned that there's a force. Okay. So I'll put the force. So there's a P force that I missed. So there's this P force, right? There's this R1, R2. So someone said, why not? So I got counterclockwise positive. I'll also do clockwise positive after, right? No problem. Let's see if I can put this chat thing also here. All right. So right now I'm doing counterclockwise positive. I'll also do clockwise positive later after I do it with counterclockwise. So this is the whole thing that we have here, right? So let's take the moment about A. Sigma M, A should be 0. So these two forces pass through A. Also, one of the components passes through A, right? So we have got rid of three forces. So let's see, this distance is L, right? Let me just check. Yes, the distance is L. So if I take the moment, I'm taking counterclockwise positive. So I first take this WL, right? Negative WL times L over 2, because WL is clockwise, right? So plus T over square root of 2 times L Then I'm taking care of this one. Then I take care of P, right? Minus P times L should be 0, right? Okay, the unknown here is this T. So if I want T over square root of 2 is equal to P plus WL over 2. All right, so let's consult our feelings about this. So we got one answer here. It is telling us that the vertical component on the right end should be P plus half of WL. It makes sense, right? So if you have this distributed load, right, you expect half of it to go here, half of it to go here. And this is what's happening. So this WL is coming from here. And there's one P, which all of it goes to this T over square root of 2, which is the vertical component here. So it makes sense, right? Any questions? You can either write in the chat thing or raise your hand. All right. So just to show that it doesn't matter which direction you take your moments. So I took this one. Let me take this one. Right. So all the signs that I have in this equation will be reversed. Let's look at WL first. So you see, this was WL. I'm taking the moment here, right? So now this is in this direction, right? WL is rotating this in this direction. So it's positive. But the other way that we took, it was negative. So if this was positive, this would be the negative direction. So let's see. We have WL L over 2 minus T over square root of 2 times L. You can see I'm on the top. If clockwise is positive, this T over square root of 2 is in the negative direction. And plus PL equals 0. So you get the exact same result. So you can see that when you're writing the equilibrium, the total equilibrium for a segment or for the total structure, it does not matter how you take your positive direction. That applies to even forces when you're writing sigma fx and sigma fy. So let's write sigma fx equals 0. So the forces that I have in the x direction are R1 minus T over square root of 2. You see, that's all I have in the x direction, right? So this should be 0. So R1 is T over square root of 2. Sigma f y equals 0. So let me sum. You see the figure on the top right, right? This figure. That's what I'm focusing on. So sigma fy equals 0, R2. R2 minus P minus WL plus T over square root of 2 equals 0, right? So R2 becomes P plus WL minus T over square root of 2, right? But I have already calculated T over square root of 2 from here, so I can substitute. So R2 is P plus WL minus P minus WL over 2 equals WL over 2. Again, we can consult our feelings a little bit. So if you have this beam here, you expect the component here to be half of this WL, right? So that's what's happening here. This is WL/2. So that's it. We have all the reactions. So we are done with step 0. So in my notes, I say that step 1 should be to choose your coordinates, but this is mainly for frames system. Because for beams, we always can assume that our coordinate system is like this, right? So we don't need to do anything for step 1. All right. So let me repeat the figure here. So I'll do this with 2 methods. So method 3 on my notes and method 1. Methods 1 and 3. So 1 is the cut method. And 3 is just the simplified, I call it, I don't have a name for it, like simplified combination of direct integration and cut method. You can call it that. So this method 3 just gives you like the geometry of the shear and moment diagrams. But the cut method gives you the actual equations, right? Okay, let's do it. So I repeat the figure. So I'm gonna use the cut method now. So I have a distributed load, right? I have a distributed load. Now I have R1 and R2. R1 turned out to be T over square root of 2. R2 was WL/2. This one was P plus WL/2. There was one P here. What else am I missing? Okay, so this is T over square root of 2. And I have 1T over square root of 2 like this. And we found that T over square root of 2 is what? T over square root of 2 is equal to R1. From here. Oh. Let's see. Any questions or comments? Let me know in the chat thing or the raising hand way. All right, we find that T over square root of 2 is, okay, this one. You see, we calculated T over square root of 2 from here. Which was what? P plus WL/2. So T over square root of 2 is P plus WL/2. All right. So if I want to use the cut method based on my coordinate system, I just have to make a cut like at X, which I make from here, right? So if I do that, when you cut something, you just separating a piece of the structure and looking at it just as if it was like an independent structure, but on its own, right? Forget about the rest of the structure when you cut something. So if I look at just the cut, so this is where I cut the thing, right? So this becomes like a new structure for me. Based on the stuff that I told you in class, like how can you tell what's the positive direction of stuff based on your coordinate system, right? So if I want to say the positive direction for shear, I can see that based on the cut, normal to the cut is T hat, right? So this is the positive direction of axial force. So normal to the cut is in the positive direction of x-axis. So shear is in this way. Moment should point in the positive direction, like the compressive side should be in the positive side. So this is the moment, the positive direction of moment. And as I said, N is like this. All right. So whenever you cut somewhere, these three pop out, right? So let me put all the forces that I have on this cut segment, right? So I'll keep this as t over square root of 2 just for simplification, but we can substitute, right? So now I have to, because the length of this segment is x, right? I have to put the force on this segment. So the resultant should be for this segment, right? So which is W times X. That's it. So I have a segment and I've put all the forces that I can possibly have on it. So I want this N, V, and M as a function of X, right? So I just have to calculate them for this segment. So let's start with N. That's easy. If I write sigma fx equals 0, so N plus t over square root of 2 is 0. So substitute for t over square root of 2, N equals minus p minus WL over 2. That's it. So I substituted t over square root of 2, which is here. Right? So that's my N. That's N. So let's go about V. So for V, as I said, we have to be smart about where we take our moment about. But you know what? For V, you just need to use sigma Fy equals 0. So if I write that WL over 2, which is this one, this one, this one. So these are the three forces that I have in the Y direction. Minus Wx minus V should be 0. So V is Wx minus WL over 2. That's it. I got V. That's V. So just to use a little bit of method 3 here, method 2 here, which is direct integration. So at this point, since I have V as a function of X, there is no problem with integrating. So you have two ways that you can get M here. You can either integrate V, or you can write equilibrium about, for example, this point, right? So writing the equilibrium is just a routine, right? Exactly the same as we used it for calculating the reactions. So let me integrate. So integral of V is equal to Wx squared. So I'm just integrating this thing, right? Wx squared over 2 WLX over 2 plus C1. Let's call it V naught. Remember, whenever you integrate, a constant pops up, right? How can we get these constants? Using the values at the boundaries, or the values at some point that we know. So in this segment, where do we know the values? So we know the value. So this is M of X, right? So we know the value of M at the left end, which is basically here, the left end, right, at A. So we have M at 0 is equal to 0 because of pin support. So the left end is a pin support, right? So the moment is 0 there. So you just substitute this value in this function that you just got. In this function, you get, so if I substitute, you get V naught Okay, so if I do that, I get V naught is 0. So I can tell you this is not correct. We've made a mistake somewhere. Let me see. So you know why I say we made a mistake? Because, okay, I think someone knows what's happened. Let me. Morgan, I'm gonna unmute you. Hey, Morgan.
Hi. I think the problem is with the shear.
Okay.
So you have the WL/2 minus WX minus V equals 0. So therefore V should just equal WL/2 minus WX. The signs are switched, I think. For your sigma Fy.
Yes, that's one problem. So thanks for that. That was awesome. So, okay, so what that does, it changes the signs, right? But there still must be one other problem somewhere. Yes, that was good catch. So let's see. You know why I say that there's a problem? Because, oh, okay. So let me see. We call this M naught. M naught is 0. That was the problem. Because this is the moment at 0, right? After I integrate. Okay, did you guys see what happened? So I had called this V naught. It shouldn't be V naught because it should be M naught, the moment at 0. So when I calculate, I get the moment at 0 is 0, which is correct because we have pin support, right? Thanks, Morgan, for finding the problem with the signs. Any questions on this? Are you guys sure? Talk to me. I don't know how you guys are feeling. Okay, I'm gonna unmute Giovanni.
Hello.
Hey Giovanni, how are you?
Hi, good. About the FY,
Okay.
aren't the signs correct before you change them? Shouldn't it be negative WX plus WL/2?
See. So this is definitely correct, right? Do you agree?
Yes.
So if I just move V to the other side, oh yeah, that's correct. The signs were correct. Right now it's okay.
Yeah.
All right, so thanks again. So I think, yeah, this should be okay. Okay. Thanks. All right. So comments. Anyone have comments? Raise your hand if you have comments, or you can even write in the chat thing. Okay, if not, let me do the approximate deformation for this one as well. So you see now I have the m of x function, right? First of all, now I have, let's say I have v of x and m of x, right? Using the cut method, you actually get the equations, right? So I got v of x is WL is L over 2 minus WX, and I got M of X is WX squared over 2 minus WLX over 2, right? So I have these two equations. So how do I understand how to like plot the approximate deformation, right? So I'm gonna give you two more equations, like so if y of x is the deformed shape of the beam. You remember from calculus, right? So it's just a function. The deformed shape of a beam, it's nothing but just a regular function, right? Just y of x. So from calculus, remember dy over dx was what? Was the slope of a curve, right? The slope of a curve, which we call, like, you can call theta, or some people call y prime, right? So basically the slope of a curve is the slope of the beam, because like deformed shape of a beam is just a function. There's nothing scary here. What about the second derivative? Now, this follows a theorem that I think in mechanics of materials you should have seen, right? It was m over ei is the second derivative, right? So I'm gonna unmute Michael. I see a hand here. Hey, Michael.
Hello.
Hi.
Yeah. For the moment function, should
Okay.
you already like switch it in the V in the upper page, but when you integrate it, I think you forgot to like switch the plus and minus as well, because it's negative WX. It should be negative WX of.
Okay. Nice. Is that okay now?
Yeah.
Nice, nice. Thanks.
And then from the bottom part also.
Yes.
Okay, perfect. Thank you.
Looks good. Thanks. All right, good. So, guys, do you remember this from like mechanics of materials? So basically, the first derivative is the slope. The second derivative is moment divided by like a positive constant, right? So basically, do you remember the concavity of a curve? The second derivative gives us the concavity of a curve, right? So if the second derivative, which is basically m over ei, is positive, it means that your curve is pointing upward. It has a positive curvature. Positive curvature, right? If your m over ei is negative, it means that your curve has a negative curvature, right? So if you want to plot your deformed shape, all you have to do is look at sine of your moment diagram. That's it. So let's plot it. So I have mx at 0 is 0. I'm plotting the moment. Moment at the other end should be 0. And like in between is, if I do like, let's put like L over 2 in the moment. Let's say m of L over 2. Or, I mean, you can do also one thing. So, so I want to plot it. Let's say I want to plot the moment. I know that it's a quadratic function, right? But what I don't know, does it look like this or does it look like this? Again, it's a concavity issue. So I'm plotting the moment diagram here, right? Just I'm saying this like as a side point for plotting quadratic stuff. So again, if I have the second derivative, I can tell you which one it is. So whenever you want information about concavity, whether something is a concave like it's concave downward or concave upward, you have to look at the second derivative. Fortunately, I know this dm over dx is v, and dv over dx equals the second derivative of moment is equal to negative w. W is negative, W is positive for beams when it's pointing downward, right? W is always positive. So the second derivative here is negative. So this one is out of the picture. So this is your moment diagram. So your moment is positive throughout the beam. So if I want to plot the approximate shape of this thing, right? So, I mean, you have this cable here, but you can kind of ignore this cable right now. So if I assume that this cable is rigid, it just means that this point will move on a circle. So if you assume that this cable is rigid, it moves on this circle. But we are also neglecting axial deformations, right? So you can forget about this for now. Okay, so let's see. I want to plot the approximate deformed shape. I know that moment is positive, right? So I can plot something like this for the approximate shape, or I can plot something like this. So you see, because of the fact that we know M is positive, this one is out of the picture. So this becomes approximate y of x. So someone has asked, how do we know that moment is positive? So okay, let's see. So one way to say how do we know moment is positive is to say I have the equation, right? So you have the equation. You can calculate m at L over 2. Let's do it. So you see, I have the equation, right? This is my moment equation. M at L is negative WL squared over 8 plus WL squared over 4. You see, this is bigger than this, so it's positive. That's one way. But let's say we want a quicker way. So let's say we want to do it like a trick or something. So you have the moment at 2 points, right? So at 2 points, because these 2 points are pins. So you want to pass a quadratic function from these 2 points, right? So you have basically 2 options. You can do this, or you can do this. There is no other way to do it, right? There is no other way to draw a quadratic function that passes through these points and have it be some other shape than this. I assure you, because this 0 point has to be between these 2 points, right? There's no other way. So if you look at the quadratic function, it can't be one of these 2 points, right? The only way that you can have these 2 points have the same y value is if this minimum or the maximum, the minimum or the maximum is between the two. So it's either this one or this one. And based on the concavity argument, we can say that, okay, it should be concave downward because negative W is negative, so it should be this one. So 2 ways you can say that moment is positive. One, look at the equation. The other one, use this trick. It's not a trick, just use the information you have from second derivative. Use the information from the second derivative. Right? Questions, guys? So yeah, so I think that's all the solution for this one. So now I want to hear your questions. Like any question you have, you can probably share your screen with me as well. If you have like a written text or something. Okay. From Richard. For frame problems, I think the professor said we should always. So let me read the question from Richard. For frame problems, I think the professor said we should always plot shear and moment diagrams with the frame always being under compression. If we follow the coordinate conventions you mentioned discussion, are the plots we make going to be okay? Okay, that's a good question. So let's see. Okay, Richard is asking about like, so in class you have heard this plot moment on the compressive side. You know, but what's the compressive side first? Like we have to understand what we mean by compressive side. How do you decide which side is the compressive side? I would say this one only works for beams because beams have a clear compressive side based on the positive convention of moment. So whenever you have a beam like this, your positive convention for moment is always this, because your coordinate for beams is always this, right? So your positive side for beams is always the top side. So the top side is your compressive side, right? But for a frame, let's say this is a frame, right? For a frame, there is no up or down. Let's take the left member. There's no up or down, right? So you're free to choose your coordinates. But there's one interesting thing that happens. So you ask, is the moment going to be okay? So let's see. If I use the thing that I said, this is X and Y. If I, let's say, make a cut here, right? So based on the convention that I said, the moment should always point in the positive direction, right? So this is the positive side. So the left side is the positive side. So this is the positive convention for moment. So if you calculate and you get moment positive, where do you plot it? Based on this coordinate, you plot it on this side, right? So you plot it like this on the left side, y, x. Now, let's say you take your coordinate the other way around. So if I had taken my coordinate like this, right? So based on the convention that I mentioned, now your moment has to again point in the positive direction of the coordinate system. So now this is your positive convention for moment, right? But for the same structure, now that you calculate your moment turns out negative because your convention has become that. So if your moment was positive here, the problem is the same problem, right? You have only changed convention. Change convention. Now the moment becomes negative. So how do you plot this? You see, now this side is the negative side, this side is the positive side. So your moment is negative, but you again end up on the left side. So you see, no matter how you choose your convention, the moment it ends up on the same side, right? But now this side happens to be the negative side. But here, this side was the positive side. So as you can see, you're gonna be fine. You'll be fine with this convention. Your moment automatically ends up on the compressive side, right? So Richard, does that answer your question? All right. So Ronnie says he has a problem with audio. Okay. Guys, other questions? So again, as I said in class, like the methods and stuff that I write in my notes and like mention in discussions. So I'll try to like give you like an alternative way from lecture notes. You can see both of them and see which one you like. It's easier for you, and then choose that one in exams and stuff. Any method that either me or the professor says is fine as regards the exams and stuff. So nothing to worry about there. Questions. So, I mean, okay, so Brian says E or I. Let's see which ones are E or I. E is this one. I is this one. So I'll do E first because E is another like a more difficult version of I, because I'll explain why. So let's see. All right. So I is very easy. You see, this is spring here. So there's one P and this is like this, right? Guys, for this problem, this is spring. You can just throw the spring out and put a concentrated moment there. Was it? Oh yeah, there was support here too. That's it. So you call this, let's call this MSP. You just solve this problem. Solve this problem. That's it. So that this spring thing is straightforward. So let's do E. I'll do E using method 3, which is like the simplest method that I know. That just gives you geometry. Just gives geometry. If the exam question is asking you to like plot or maybe draw shear moment, it means that you don't need to like get the actual equations, right? If you want equations, which probably maybe one of the questions will have, you will have probably both kinds, right? If you just want the shear moment, like if you want to just plot or draw the shear moment diagram, you just need the geometry, right? This method 3 is really good for that. So let's see problem E. All right, let's do E. 2L, so it was like this, right? PL, and there was P here. Nice. So you'll see how fast we can do this. So step 0. Step 0. Reactions. Do you remember from degree of indeterminacy stuff that we said we have a constraint here? And I said that constraint just means that you have an extra equilibrium. equation. So basically, when we want to solve problems that have these constraints, we have to like come up with a way to use these extra equilibrium equations to find our forces and stuff, right? So how we do that usually is that we cut the structure at the place of these constraints. So okay, so I want to find the reactions, right? So if I look at this right side, if I look at just the right side, so if I make a cut just to the right of this, let's call this A, B, and C, just to the right of B. So when I cut here, because of the constraint, right? Because of the constraint, so let me call this like R1, R2, M, I call it ML, and this can be R3. So this is R3. So because of this constraint, moment is 0 here, right? So this M equals 0 is basically an extra fact, an extra equilibrium equation that I can use, right? So when I cut here, F1 and F2 jump out. So if I take the sigma M around like this point, if I call it like B equals 0 for this segment, right? This, I've cut this out. Oh no. Let's see how I can go to the next page here. Okay, nice. So I've cut this segment out. So these F1 and F2 are basically internal forces here. So if I write sigma MB is 0, so you see, again, as we saw, we can take any as positive, any direction as positive. So I take counter. Try not to get too used to like, try to like alternate so that you don't get too used to like one particular direction, so that you think that you always have to take that direction as positive. This is completely arbitrary, right? Remember, this positive convention has nothing to do with the convention we have for internal moments, right? It's completely a different thing that we use in each situation to just sum the total moment on the structure. So if I do that for this part, I have 1 PL here as well. So based on this positive direction, PL plus LR3 is 0. So R3 is minus P, right? So I got R3. Now, basically, I've used my extra equilibrium equation, right? So I could calculate F1 and F2, right? But for now, I don't seem to need it, right? So I go about calculating the total stuff. So now I look at the total structure. If I plot the total structure, I have R3 equals P. So I have 1P here. I have PL. I have R2. I have R1. I mean, since this is a beam, you don't need to put the horizontal component of reactions, right? If you see that no external force is horizontal along the beam, you don't need to even put the components of the horizontal component of reactions. So I just got rid of that one. So I put this as MF. All right, so sigma Fy is 0. So negative P minus P plus R2 is 0. R2 is 2P. All right, if I take the moments, okay, so here you can do two things. You can again cut at B, I'm gonna do this, like cut at B. So I have ML, I have R2. I get a couple of forces here, right? But I don't care about this. So I take the moment about this point. So I'm kind of using again the extra fact about this point, but now for the left side instead of the right side. So if I do that, sigma MB now to the left, right, is 0. So I get positive, let's take this one now. 2L R2, this length is 2L. 2L R2 plus ML should be 0, right? So ML is negative 2L R2. And I have R2 from here. Gives me ML negative 2L 2P. Negative 4LP. Negative 4LP. Let me know if I make a mistake or something somewhere. Negative 4LP. So let me put all the stuff that I've calculated on the structure. So I had an external PL, right? I calculated R2 as 2P, right? I calculated negative 4LP for here. I changed the sign for LP. I had 1P here. I got this one, which should be P. Okay, something's wrong. Okay, now it's right. So it should be negative P. I changed the sign, right? Let's do a quick check. And this is 2L, L. So I have one P downward, 1P downward, 2P upward. So it's fine, right? At least sigma Fy is okay. And the moments are also okay. You can do a final check, like take the moment for the whole structure if you want to be absolutely sure. Let me just do a quick check. 2P, yes, it's fine. Okay, so our reactions seem to be correct. Okay, Brian is asking, how did you calculate R3 to be pointing downward? Did I have R3? You mean R2? Oh, R3, okay, the right one. So let's see. Come on, what's happening? Where was R3? R3 was the right one, right? So this was R3. So you see, initially I assumed that R3 is upward, right? Initially I assumed that R3 is upward. I calculated, I got R3 negative P. So it means that my initial assumption was the opposite assumption. So I can either put it like this, or I can change the sign and put it as P. And that's what I did. Does that answer your question, Brian? Okay. So Chris, I see your hand is up. I'm gonna unmute you. Hey, Chris.
Hello.
Hi.
So I had A question about the very first cut you made, right under where it says step 0 reactions.
Okay.
I'm just wondering, why are you able to move R3 and PL to where that hinges? And why is P not there anymore?
Okay, that's a good question. So you're saying when I'm cutting, right? Why did I just forget about P,
Yeah.
right?
Well, that and why are the other two, like the moment and the R3, able to be moved to where P was also?
You mean the right side?
Yeah.
What do you mean we moved them? We didn't move them.
Hmm?
So you see R3 and PL are this point,
Yeah.
right? So I've put them exactly where they are applied. Do you agree?
Okay.
So the only thing, why did I not put this P here?
Mhm.
Right? So the reason is it doesn't matter. So you can imagine like this. Imagine that I'm making the cut just a tiny bit to the right, right? So if you make the cut a tiny bit to the right, then there is no P on this segment, right? But even if you put this P here, because I'm taking the moment about this point, the P passes through this point, right? Nothing changes. It doesn't change anything.
Oh, I see.
Do you agree?
No, actually, I was looking at it backwards.
You mean probably mixed with the left side?
Yeah, I got the left side and the right side mixed up. That's
Yeah,
why I was so
but the left
confused.
side is also the same. Like you see, I didn't
Yeah.
put the P here, right?
Yeah.
Here. But if you put the P here, because you take the moment about this point, it doesn't make any difference.
Okay.
Right?
Yeah.
All right. Okay, thanks, Chris. Guys, let me know if at any point you have questions or something. All right, so this is the final product for the reactions, right? I have put all the reactions and external forces. So for beams, N would be meaningless basically because we don't have axial forces in beams, so N is 0 for beams. Be careful that you don't have any axial stuff. For example, in the rope example, do you remember like the rope one? We had an axial component, so we had to write N as well. But here it's just a beam. All the forces are vertical forces, right? So you don't have N. So let me use this quick method to calculate V. So this quick method that I'm saying, it just gives you the geometry. So how do we do this? So I have to chop this into segments. So this is the first segment. You shouldn't have any concentrated load along the segment. So I take it from 0 to L, right? So I know that 0 to 2L, the first segment, right? Basically the first segment. I know that along this segment, W is 0. So V, which is the integral of negative W, should be a constant. So I know based on this, without doing any calculation, whenever you have a segment without any distributed load, it means that V is a constant, right? So you have this information. What can I do with this information? So basically, when V is constant, if you have the value of shear at one point, you can plot it along the whole member. You have all the V that you want. So is there any point that I have the shear values? Yes, there is, because I have calculated you see this point? Because I have calculated the reaction here, I already have the value of shear at this point, which is 2P. You agree? So the only thing is that I have to be careful with the signs. So is this 2P positive shear or negative shear? So I know that this is my coordinate system. So again, I'm going based on my own thing. But for beams, you can just memorize the lecture convention. That's also totally fine. So I say, okay, this is my coordinate. T hat is in the negative direction. So this is the direction of positive shear, right? So you can see that 2P is in the direction of positive shear. Nice. So I have the shear in this whole segment, basically without doing any calculation. So let me clear this stuff. Okay, so I have that's it, 2P positive. All right, how about the other side? Again, for the other side, there is no distributed load, so I know that there's a fact that shear is constant. Now I have the shear again at one point of this segment, the right segment, which is this point. Is this shear positive or negative? Again, since your coordinate is like this is T hat, it's pointing in the positive X direction, so this is the direction of positive shear. This P is in the positive direction of shear, so it's positive. So the value of shear for this segment is positive P. Done with shear. So you see, without doing any cuts or calculation or anything, you get the geometry of this shear. Be sure to put the values at the ends on your graphs, right? Even if we ask for like, if we say like draw the shear moment diagram, you have to put the values at these points, right? So let's do moment. You can do moment like this. So now that you have shear, so shear is constant, right? So M is the integral of V. So shear is constant. So moment is linear, right? So again, if I want to plot a line, I need 2 points of the line, 2 points, right? So do I have 2 points? So the first segment, the second segment. Do I have the moment here? So the positive convention is like this. Do you see this 4PL? So again, based on the, oh, what's happened? Okay. So this 4PL, right? Based on the reactions that I calculated, I know the moment at that point. Okay, so I know that moment is negative because it's like the 4PL that I have is in the negative direction. So you just plot the 4PL, negative 4PL. I know that moment is 0 here. So I have 2 points along this segment. That's it. You have your moment for this segment. Do I have moment at the other end? Now here, the positive direction is like this for this point, right? And there is a concentrated external positive PL here, right? So again, I know at this point it's 0. I know at this point positive PL. That's it. Now, how about the approximate deformed shape? We said sine of M. That's all we need, right? So you plot the original shape of the structure. Okay, I want to plot the approximate deformed shape. So Ronnie asks for F. Does the roller only express Fy? So Ronnie, do you mean for this problem? Oh, you mean the one that has a rope? Oh, no, for F. Okay, so I'll get to that one. Yeah. So I'll get to that one. So let's do the approximate shape for this one. So if I want to start from here, so you see that the fixed support, the tangent should be horizontal, right? So you can either start this way or you can either start this way, right? As we said, the second derivative is the moment, right? So the moment along this one is positive. So, sorry, it's negative. So the moment along this segment is negative. So it cannot be this one. So there is only one way I can think of to plot this. Start with a tangent horizontal here, go down here, right? So how about this segment? First, I know that it should pass through this point. It should pass through this point. It should be quadratic. It should be, I mean, we don't care about like the degree. It should be actually degree of 3, but it's doesn't matter. We just need the approximate shape, right? So M is positive here, so it should be concave upward, right? This is the approximate shape. You see how easy it is? So you just look at the sign of M, and that's it. Any questions about this one? Talk to me, guys. If you have questions, just let me know. All right, you're welcome. So let's move to, okay, problem F. So Ronnie is asking for F, does the roller only express an Fy at 45-degree angle? Okay. So let's see. So what's the problem? Okay. So this is problem F. So you see, when you want to solve these frame problems, it's a totally different game from like the stability problems that we have, right? You can't simplify the structure or anything. You have to consider the original structure completely. So, and when you have these rollers, the direction is very important, right? So when you have a roller that's like horizontal like this, like the ground is with this degree, so the force that this one applies is just this. So you have R1, R2, RM, 1M, and I call this R3, right? So on this segment, you just have one force, right? Again, now this becomes just repetitive, right? So step 0 is again the same. So do you remember that this problem we solved earlier? Exactly this problem, right? How did we handle this pin? It's basically the same. Whenever you have these pins, you separate them at the pin and use a moment about that pin. I think I can say that that's always the case. So again, if I separate this right side, so like exactly like the previous problem, F1, F2, you see, if you practice, like these issues keep repeating themselves, right? They are finite. So R3, right? If you take the moment about this point, R3 is 0. So basically this member is useless. So because there is no force, this one is 0, right? So if you make a cut somewhere along X, there is no force, right? So if you make a cut, like whatever coordinate you get, right? For example, however you put these, N0, M0, V0 for this segment, right? And the other, so basically your problem becomes a cantilever with a distributed load, which is simple to solve, right? Now, if you want to challenge yourself a little bit, I mean, if you want to do the conventional way, it's fine. You take your coordinate from here and you go ahead. You first calculate the reactions and like make a cut or something. That's fine. But in this particular case, I would say it's easier to take your coordinate from here, right? If you see this makes you confused, forget about it. But taking your coordinate from here, if you want to use the cut method, could be a bit easier, right? And be careful that whenever you like put your coordinate here, your origin of your coordinate is here. So when you take x, now this becomes your x, right? So the equation that you get for this beam for M and V is different when you use this coordinate or this coordinate. So you get different equations. Don't be surprised if you get different equation when you use this coordinate or this coordinate, right? So Ronnie, does that answer your question? Okay. So questions, guys, talk to me. If anyone has any questions. Oh, okay. Landon, I'm gonna unmute you. Hey, Landon, how's it going?
I'm good. So for the spring problems, H and I, to
Okay.
solve for the reactions, do we have to do the slope deflection method where we like use
No.
superposition?
So for these problems, so you see, as I think I solved the I1, right? I said you can just assume that there's like a concentrated moment here, right? Call it like MR and solve your problem. For this one, assume that there is a concentrated force, call it F and go forward. So basically your problem becomes this.
So we don't treat those as unknowns. We just call it F and solve.
Exactly, because
Okay.
you haven't learned yet how to calculate deflections, right? You will soon be able to
Okay.
do that, but not now.
Sounds good.
Yeah.
Thank you.
Okay, sure. All right. Alvaro is asking, problem H, is there a moment at the middle? Problem H, oh no, there's no moment at the middle. As I mentioned here, there's just one vertical force, right? For H. Does that answer your question, Alvaro? Okay, nice. So, all right, one of the book questions, 438. So the thing is, I'm not sure if I have the book problems in front of me. I think I might have a PDF of the book somewhere. $438. So yeah, I'm trying to see if I can find the problem 438 from the book. It's just opening. Oh yeah, I have the PDF, so yeah, I can do this. So let me see. 438. Best thing to do is to search for it. 438. Just go down. Okay, I found it. So let's see how it looks. 438. It's this one, right? Oh yes. Draw the shear and moment diagrams. For each of the three members of the frame, assume the frame is pin connected at A, C, and D. Okay, it's not too difficult. Okay. So let me put this here. All right. So first, these book problems are like weird looking, right? So let's put it in a form that we have seen in class, which is like simpler. So what's the vertical? Okay, so this is just 5. So this is 4. This is 5 meters, and this is 6. So whenever you see these book problems that are like, I mean, they have tried to be more realistic, but in my opinion, this is much simpler. So yeah, you see, it said A is also pin connected, right? A, C, and D is fixed at B. So A is also pin connected. Okay, this is a good question. So if I also like put two forces, one, because okay, so one of them is 50, one of them is 50, one of them is 40. Let's say this is A, this is B, this is A. So these have numbers, right? But what you can do is like you solve it parametrically. I think that would be simpler to solve it parametrically, to not like your intermediate calculations do not have to like go through the calculations, right? So you can solve it parametrically and at the end substitute. I think that would be much simpler. That's what I'm gonna do. So I put like these distances as ABC. I'm gonna put this as L1. Like I can call this like AB. Let's call this C. Let's call this D. Or you know what? Because it has many parameters, it's gonna get a bit too difficult. So let's do it. So based on the Ronnie is asking, aren't they fixed? So you see, the problem is saying assume the frame is pin connected at C, A, C, and D, right? And there's a fixed joint at B. So this is the only way, that only place that's fixed, right? This is a joint, this is a joint. Yes, okay, nice. Oh, a fixed joint means that your structure is basically continuous. So Brian is asking what a fixed joint means. A fixed joint means what we show in class like this, right? There is no pin. That's it. So this is a pin. This is a pin joint. This is a fixed joint, right? Does that answer your question, Brian? Okay. So let's get to it. So for this one, I'm going to calculate the reactions, which I think that's probably the, so you can use method 3 for this one. So let me make this bigger. Okay, now that it's in this form, we know how to solve it, right? So this is in the in the form that we have seen in lecture notes. So you can use just method 3, get the values at boundaries, and figure out how the variation is, and plot the thing based on that. So step 0. I think the challenging part is step 0 for this one. So if I call this A, B, C, and D. So let's put the reactions on this. So I simplify it a little bit. So I put R1, R2. So Brian is saying, can we treat ABC as one member? Brian is saying, can we treat ABC as one member? No, that's a no, because you have a joint in the middle, right? So ABC, you have to treat AB as a different member and BC as a separate member, right? Okay, so I think that was the question, right? So can we treat ABC as one member? I would say no. You have to treat AB as one segment and BC as a separate segment. All right, nice. So, all right, so I have these two forces, like 50 and 40. So let's see how we get these reactions. So you see, again, we have seen 2 examples of how to deal with this so far. You have a pin, right? So we have seen 2 problems that have these pins. The procedure is exactly the same. So I separate this right member. So if I separate this right member, so I have R3, I have R4, I have F1. So you see, when you separate these 2 forces jump out. I have F2. For this problem, I don't think you can avoid 2 equation, 2 unknowns, right? Oh, okay. I just saw it. Thanks for the distributed load. Yes, so there's a distributed load. I'm gonna put the resultant, right? I'm gonna call it this resultant 6 times W, whatever it is, right? So there should be 6 times W. Right, so for this problem, I don't think it's possible to avoid 2 equation, 2 unknowns, right? So, but it's okay. So if I take a moment about what's this? A, B, C. This is C, right? A, B, C, D. So if I take the moment for this right segment about C, so, oh, we might actually be able, well, maybe we'll be able to, we'll see. So if I take the, so it becomes, so I take the positive like this, right? So this 6 times W is in the negative direction, so it becomes 6 times W times half of L, which is 3, L over 2, right? Plus 6 times R3, and the rest pass through C. right? So you get R3, 3W, right? So how do we get the rest? Yeah. So Ronnie is saying it's 15 kilonewton per meter. So, but I took it as W. You can substitute at the end, right? You agree? So I just took it as W, and you can substitute at the end, right? Yeah, nice. All right. So I have an idea to like. Okay, now I looked at this segment separately. Now I'm gonna look at the whole structure. So you know where I'm gonna take moment. So I'm gonna take a moment about this point, right? Again, we take moment about places that like take care of, like most forces pass through, right? So Giovanni is saying, isn't 3 times 6W positive? So let's see. So you see, I took this as positive direction. So I'm taking the moment about this point, right? So 6 times W is rotating this thing in this direction. And so this was my convention. You see? Do you agree? Nice, no problem. Okay. So let's see. So if I take the moment about this point, so this distance is 2, right? So this distance is, so I mean by this distance I mean to here, right? And this distance is 1, right? So sigma m over a is gonna be a bit, I think, long. So 6 times W times 1, which is this distance, right? 6 times W times 1, negative 1.5 meter, which is this distance, right? Now this is in this direction, so it's in the negative direction of our convention. So minus 1.5 times 50 minus 3.5 meters times 40. So this was 1.5, this was 2 meters, right? You see, 2 meters, 1.5. 2 meters. I took care of the distributed load. Okay, now I have to take care of the R3. So R3 is 2 times R3. It's in the positive direction. You see this one? I'm looking at R3. So R4 also is in the positive direction. Plus 5 meter times R4 equal to 0. Right? So I have R3 from here. So if you substitute for R3, you get R4. Right? R4. Now the rest is easy. Sigma fx, I'm not gonna write it because 0 gives R1. Sigma fy equals 0 gives R2. Right? Unfortunately, I'm out of time, kind of. I'm not going to continue this problem to the end, but I guess the hard part for this one is calculating the reactions. If you have those, then the rest is exactly similar to what you had in your previous questions. If you see that just the actual numbers are bothering you, you can solve it symbolically and substitute for everything at the end, right? But one good thing about having numbers is that like you can simplify along the way and things look a bit more compact, right? All right, guys, I hope this was useful. If you have suggestions about these online things, this is the first time I've done the online thing. So let me know if you like it or not with emails, or if you have suggestions, comments, and stuff to improve it. Let me know through email. So you're asking if this will be weekly. If you like it, I wouldn't have a problem with making it weekly. I did this as an experimental thing to see if it's useful. If it was useful, then sure, I can do it weekly. Yeah, sure. Okay, seems like you guys liked it, so I'll probably make it a weekly thing. Okay, about review before quiz. Probably I'll have like one extra session before the quiz, but yeah, I haven't decided yet. I'll let you know. I'll let you know. All right, guys. I hope you liked it. So I'll probably make this a weekly thing. We'll see. I'll let you know through email or announcements in Canvas. All right. Have a good weekend and see you later. Bye. الان آقا همین الان تموم شد. کجای الان؟ ها ها طول کشید خیلی طول. کجای الان اینجایی؟ ها اومد. او آقا من یه دقیقه دیگه میام. خوبه؟ ببخشید دیر شد. باشه الان میام. اوکی.